2.1, which is about average and instantaneous velocity. Okay, I'm going to introduce some more concepts like I did the other day in class. This is instantaneous velocity. And I'm going to start with a video from YouTube, but please understand that I'm not advocating whatever is being shown in this video. I'm just using it as an illustration about the mathematical concepts that we're looking at in this section. So I'm going to play this video and then I'll rewind it as we want to discuss. You'll see a person leap off this tall structure and into the water. Okay, and what happened here, what we need to look at is clearly they started to pick up velocity, and the question is, how fast were they going when they hit the water? How high is this object? Okay, so let's run this frame forward, and let's just say that we're going to see them, we saw them fall into the water. This is the height y, and this is time t. And they're at some height that we don't know how high they are. And let's say that at t equal to 0, that's about maybe 20 seconds. Maybe just 20 seconds in the YouTube video down here, 21 seconds, maybe 20 seconds right before he left. And the person is going to fall, and bang, they hit the water at about 22 seconds. So about 2 seconds later, 22 seconds in the YouTube video, they went from some height and they hit the water here. Okay. The question is, they started at 0 velocity. So the initial velocity was equal to 0. They weren't falling down this way. They weren't propelled downward. They just kind of leapt and then let gravity let them pick up speed. So gravity is pulling them down, right? So an interesting back of envelope calculation, which just means a calculation that you can do without a calculator or pencil, and just with pencil and paper, to impress your friends or whatever you guys want to do with it. Notice that if we want to figure out how high the object was, there's a physics formula, 1/2 gt squared. This is assuming a 0 initial velocity. That they fell, the height of this object was 1/2. And gravity, let's approximate this with gravity about 10 meters per second squared. And they fell for about 2 seconds because we were able to figure that out from the video that somebody took. So we have to do 2 seconds squared. So this will give us 1/2 10 meters per second squared, and then 4 seconds squared. Okay, which is equal to 1/2 40 meters. The second squareds cancel out, and so therefore they fell about 20 meters, which if there's like, maybe this is a guesstimation, 3 feet in a meter, around 3 feet equals 1 meter. That's just an approximation, somewhere in that vicinity. They fell about 60 feet. Okay. And this is all very approximate, but kind of gives you the idea of about how far they fell. So let's take a look. This physics formula, if you've had the opportunity to take physics, probably looks familiar. And this calculation is a function which tells us y of t. T is the variable. G, or gravity, is a constant. So this is just a function y of t. Gives you the height at any time, the height above the water. Okay. So let's bring in some more numbers here. I have a document that we kind of looked at, very similar to what we looked at the other day in class. So let's take a look here. Here I've just got some data. We know from this calculation that they were initially up about 60 feet. So why don't we change this number to 60? Okay. And they had an initial velocity of 0. And let's assume that the person watching them has a camera that can take a picture or something about every 0.5 seconds. Okay. And I think we can see here that 0.5, here's the plot that we are seeing. I think we can see that they're at a height of 60 and they're falling. So there's a little snapshot of the little person here, snapshot. And about 2 seconds they hit the water, right? And here is the data that we are seeing. Let me put some numbers over here on this side. So what we are seeing from this data over here is that their y and t, they hit the water at about 2 seconds. So what I'm kind of interested in is how fast was the person going when they hit the water. Okay. I'm sure there's a maximum velocity that is safe for human beings hitting water. I'm sure somebody's done that calculation. Look it up on Google if you're interested in. But let's take a look at how safe this jump was. I'm not saying it was safe or not safe. I'm, again, not advocating jumping off those things. I'm not particularly a fan of heights myself. But let's take a look at what's going on here. About 2 seconds. Okay, they're at about a height of 0. And at 1.5 seconds, they were at 24 feet above the water. Okay. Now let's take a look at here. This number, negative 56. So if you look at their average rate of change from t is equal to 1.5 to t is equal to 2, right? That is telling us that their average rate of change, if you did 24 minus y2 minus y1 minus negative 4 divided by 1.5 minus 2, you should get this number, negative 56. This says that they were going down 56 feet per second. So that's about how fast they were going according to this data, right? It's a very, is this the best number we can do for figuring out their average velocity, right? Well, if you can increase the number of frames that you can take in your video, let's up the time spacing. So watch what's going to happen. Let's say that you can have a camera that can take their position every 0.25 seconds. So every quarter of a second, you've gotten a better camera. Let's change the time spacing here to be 0.25 seconds. Okay. And in here, we've only done six of these 0.25 seconds, so that only brings me to about 1.5 seconds. So if I increase the time here, right, we're seeing that they're still hitting at around 2 seconds. Okay, and let's increase the time here to get some more data. Now let's take a look here. The average rate of change, according to this, the average rate of change from t is equal to 1.75 to t is equal to 2. This is the time we're interested in, right? They hit about 2 seconds, so we'd like to find their average rate of change from 1.75 to 2. This is the number we're really interested in. So if we take a look here, this number minus 60, they're going down at 60 feet per second. So notice that just by changing the time spacing, we've upped their velocity just a little bit. Here is their speed. And the down you put those two together and you get velocity. So velocity is the direction that they're moving and the speed. All right, so let's do one other measurement here and let's see if we can get a good idea. Let's just say that we've gone out and bought the most ridiculous camera we can find that can take an image every 0.1 second. 0.1 second. Sorry, let me type this in. 0.1 second. If I can get my act together here. 0.1 second. 0.01 seconds. Okay, what's going on here? There we go. So every 0.01 seconds. About 0.05 seconds. I have a reason for picking 0.05. So notice now if we can increase time. It looks like in this I'm only allowed to go, there we go, 100 units of 0.05. And here you can see what's going on at 2. Okay, at 2, they're about at -4, so that's essentially they hit the water there. Okay, so if we look at the average rate of change from t is equal to 1.95 to t is equal to 2. Again, we're interested in this 2, but to do an average rate of change, we need 2 times. And notice that the time spacing here, delta t, is equal to 0.05. So we're getting really close, the time spacing close together. And if you do those numbers, you should get the average rate of change to be about down. And you should double check what numbers I'm using here, but you'll get down at about -63.2 feet per second. So I'd say this number right here is really about how fast they're going. This is getting very close to telling you to how fast they're going to velocity. This is very close to the velocity at the moment t is equal to 2. Right? So I would say 63 is getting really close. 63 is really close to what's called the instantaneous velocity. If we want to get the instantaneous velocity, you have to decrease the time size here. The closer you get to the delta t equal to 0, to get the actual, let's go over here, to get the actually get the instantaneous velocity, you need to use delta t equal to 0, or getting close to 0. And this idea sets up the concept of what we're going to talk about in section 1.8, which is the concept of a limit. What we're limiting on is in the first example I did over here, delta t was equal to 0.5. So we went from delta t equal to 0.5. We then went to delta t is equal to 0.25. We then went to delta t is equal to 0.05. I can't remember what that was. 0.05, right? And presumably if you did delta t, that's what we showed. If you could go to delta t equals 0.01, delta t is equal to 0.0001, you're going to get a much better idea of how fast this person is going when they hit the water. But I'm going to say they're going about pretty close to 63 feet per second, and I'll leave it to you all to tell me if that is a good number for human beings and internal organs, I guess. All right, well, that's enough on this video. I hope I've kind of given you an idea of the instantaneous and average velocity. We'll talk more about this in class.